Hello, and welcome to another episode of Maths in an Empty Classroom with me, Mr. Sutton. This is part one of the lesson on implicit differentiation, and in this video I'm just going to be explaining how implicit differentiation works and going through the first example. So, first thing, I'm just going to start with a very simple function, y equals 3x squared. And if I asked you to differentiate this with respect to x, I'm sure that you would know that you would write dy dx equals 6x. And what I think students sometimes don't realise when they're doing this is that in addition to differentiating the right-hand side of the equation, you are also differentiating the left-hand side of the equation. And when you differentiate y in terms of x, you get dy dx. And I think explaining this really helps to grasp the concept of what implicit differentiation is actually doing. So if, for example, instead of y, we had y squared, and if we had a function such as 3x plus 2 to the power of 5, looking at the right-hand side of that equation, if we were going to differentiate that, clearly we'd be using the chain rule. So we would be saying that it would be 5, 3x plus 2 to the power of 4, and then we would be multiplying that by the differentiated bracket, which would be 3. And that would give us, as a simplified expression, 15 lots of 3x plus 2 to the power of 4. But what we need to think about is that we are actually differentiating the left-hand side of the equation as well, and we're using the chain rule in this case too. How I'm going to demonstrate that is if you bracket the y, so you now think of the y as being a function being squared. If you were to differentiate this using the chain rule, then in the same way here as we brought down the power and reduced the power by 1, we could be doing the same thing to that y, and then multiplying by the differentiated bracket in the same way as we multiplied here by 3. Now when you differentiate y with respect to x, you get dy dx. So what I would now have is 2y dy dx equals the right-hand side, 15 lots of 3x plus 2 to the power of 4. And if I now wanted an expression for dy dx, I could divide through by the 2y, and I can say that dy dx equals 15 lots of 3x plus 2 to the power of 4 all over 2y. And what that would mean, if I was now going to try to evaluate dy dx to find the value of the gradient at a point on the curve, I would need both the x-coordinate and the y-coordinate of the point that I was working with. But I think the key point to take from that is that if you were differentiating a y term in terms of x, you differentiate how you normally would, so y squared goes to 2y, but you also have a dy dx term with it because what you're doing is you're using the chain rule. So let's just go through one example. I've got here, given that 3x squared plus 2y squared minus 4x plus 8y equals 7, find dy dx in terms of x and y. So I'm just going to rewrite that function, 3x squared plus 2y squared minus 4x plus 8y equals 7. And just in the same way as polynomial differentiation, you can differentiate a term at a time. I've just got to be careful with the ones that are in terms of y. So 3x squared is going to differentiate to 6x. 2y squared is going to differentiate to 4y dy dx because I'm differentiating in terms of x. Negative 4x is just going to differentiate to negative 4. 8y is going to differentiate to 8, but I will also have a dy dx with that term. And that is going to equal 0 because when you differentiate constants you get 0. But what I've been asked to do is to find dy dx in terms of x and y, so I now need to rearrange this so that I can make dy dx the subject of this expression. So what I'm going to do is I'm going to leave the terms with a dy dx on the left-hand side, so that's 4y dy dx plus 8 dy dx. And I'm going to move the other two terms over to the right-hand side of my equation, which gives me 4 minus 6x. I want to make dy dx the subject of this, so I'm going to factorise dy dx out on the left-hand side, giving me 4y plus 8 inside my bracket. Still equals 4 minus 6x. I have not changed the right-hand side. And then all I'm going to do is divide by this bracket. So my expression for dy dx is going to be 4 minus 6x over 4y plus 8. And I could simplify that expression because each term has a common factor of 2. So dy dx would equal 2 minus 3x all over 2y plus 4. And as I said earlier, if you wanted to evaluate the gradient at a specific point, you could substitute in the x-coordinate and the y-coordinate of this expression, and that would find you the gradient at that point on the curve. Join me in the next video where I'll go through another example with slightly more complicated differentiation involved.